Here we'll look at a special property: bases satisfy, all bases satisfy. The systems of vectors, which we call bases, they are always linearly in linearly independent systems of vectors, but it's easier to start with the opposite, dependence. Linear dependence or linearly dependent systems of vectors is what is we define first. If we have a collection of vectors, we say that a linear dependence is some linear combination of them being equal to the zero vector. And of course, we always have such a linear combination. We can just take all the coefficients to be zero. So vectors are linearly dependent if we have something more interesting than just trivial solution for that. If there are xi's not all equal to zero, such that this linear dependence happens. And that is what should not happen for bases, because if we have a basis, then any vector, including the zero vector, has a unique presentation as a linear combination. If we look at a presentation of the zero vector in a basis, it must be with all coordinates being zero. So the coordinates of the zero vector in any basis are always zero. That's why linearly dependent systems of vectors are just opposite of bases, are just something which bases never are. But still, this linear dependence is as an opposite to linear independent systems of vectors is a useful concept. Let's look at an example. How practically to see if there are any linear dependencies between given vectors. So let's imagine three vectors, each of them with three coordinates, something like that. v1, v2, v3. And the typical question, are these vectors linearly independent, or are they linearly dependent, or find all dependencies between these three vectors? So let's just write what it means for these vectors to be dependent. Let's write a linear combination with arbitrary coefficients of these three vectors, and when we do this vector arithmetic, when we multiply v1 by x1, v2 by a number x2, and v3 by its coefficient x3, and when we can compute the sum of the results, we will have x1 plus 4x2 plus 7x3 in the first coordinate of the result, 2x1 plus 5x2 plus 8x3 the second place, and 3x1 plus 6x2 9x3 in the third coordinate. That is just because of the usual rules of vector arithmetic. We multiply by x1 all the three components of the first vector, the same with the second and x2 and x3, and then we sum up their coordinates. That's what we'll have. So linear dependence will be a vector equation. This interesting vector is equal to all zero vector. And this vector equation is a system of three equations, one for each coordinate. So we have a linear system, a homogeneous one, because again, every coordinate is a linear expression in the unknowns. And the unknowns for this problem are the coefficients in the linear expansion, in the linear combination. So to find all possible coefficients, all possible linear dependencies, we have to solve a homogeneous system. The standard method of solving such systems is by Gauss elimination done with a matrix. And if we look at what the matrix of this system is, it will be just the matrix built out of these three columns. So the matrix of the homogeneous system we need to solve to find coefficients in linear dependencies is this matrix. And Gauss elimination, we can start with eliminating 2 and 3 in the first column, row 2 minus twice row 1, row 3 minus 3 times row 1. We will have zeros. And then in here 5 will be changed by negative twice 4, so negative 8. 8 subtracting from 5 give us negative 3. So in this position 8 minus 14, it's negative 6. So here we will have 4 without 3 times, sorry, 6 without 3 times 4. 6 without 12, this is negative 6. And here we have 9 without 21, and that is negative 12. And we do have an interesting solution of this homogeneous system because the matrix is degenerate, the determinant is 0, there will be 0 row in the row echelon form. We could see it, we could create it by doing this transformation, row 3 minus twice row 2. Row 3 is just twice row 2, so if we do that, we will completely erase the third row. Then we can make our second pivot look better by dividing by negative 3 our row 2. And that is a row echelon form already, but we will need to reduce it to see the answer clearly. So row 1 minus 4 times row 2 will be this reduction process. Will create 0 above the second pivot, and here we'll have negative 1. So the system behind this new matrix is as follows: x1 minus x3 equals 0, x2 plus 2x3 equals 0. These are the pivots. Whatever is not is a free variable. We have one free variable, we have one parameter solution. So if we just rewrite this equation as answers for pivots in terms of the free variable, we will have these answers. And it says now, going back to our original question, it says that yes, these vectors are linearly dependent. Linear dependence, a typical, a generic linear dependence, is this solution. So anything for x3, but x2 and x1 are just like in here. So we can write this generic dependence. x1 is just x3, x2 is negative x3, and x3 is what it is. And it will be always 0. That's what our computation says. We could just take this arbitrary x3 and factor the x3 out. So we'll have, so to say, basic linear relation between our vectors. And alternatively, we can just write it as the answer for this twice the second vector is the sum of the first and the last. And we could see that indeed if we take the sum of the first and the last, we will have twice the second coordinate. Again, 2 plus 8 will be 10, it's twice 5, and 3 plus 9 rather is 12, it's twice 6. So that is a basic linear relation, that is a basic linear dependence between our given vectors. They are linearly dependent. Another example where we will see in practice we will see linearly independent system coming naturally, even the basis. So let's just find linear independent basis solutions of a homogeneous system. Imagine a homogeneous system where we will have to have interesting solutions. So that means that we should have free variables. The easiest way to create them is to have fewer equations than unknowns. So I'll have 4 unknowns and I'll have just 2 equations on them. So something like that. With these linear systems, we are inevitably we are bound to have free variables. Let's see how many exactly. So let's write the matrix of this homogeneous system. Nothing to extend it by, and start bringing it down to a reduced row echelon form. So the first transformation is row 2 minus row 1. We'll have 0 below our first pivot, then we'll have 1, and 2, and 3 in the second row. That is already a row echelon form, but just one more move to reduce it. Get rid of the number above the second pivot, and we'll have the answer being -1, -2 here. So that is it. That is saying that I will write immediately the answer for x1 and x2, which are our pivots. x3 and x4 are free variables. So in terms of these free variables, x1 is x3 plus 2x4. X2 is twice x3 with minus sign, and with minus sign 3 times x4. That is just rewriting the linear equations behind the system. And the generic solution written as a column vector becomes the following. So x3 and x4 are free. We don't have anything restricting them. x2 is -2x3 -3x4. x1 is x3 plus twice x4. So that is a vector form of a generic solution. Now we could really do something like here, but in reverse, write it as a linear combination of very specific vectors. And the coefficients are just these parameters. So we just can group every occurrence of x3 into one vector. And the coordinates will be 1 and -2 and 1 and then 0. And then x4 times vector will be what is left. And x4 will be seen in these terms. And now we are saying that any solution is a linear combination in a unique way, because x3 and x4 are free. We can choose them whatever we like. They don't talk to each other. There is no relation between them. So these two are the basic vectors corresponding to these coordinates. These x3 and x4 free variables are coordinates of the solution space of that linear system. And these two vectors form a basis of the solution space. And finally, the dimension of the solution space is 2. dimension is already visible at this step when we saw, or even at this step when we saw that we have two pivots and two free variables. The dimension of the solution space is 2. That is it with the example. See you later.